Hello. So, to continue with our pattern recognition, in the first two lectures, we have gone through a general overview of pattern classification. We looked at what is the problem of pattern classification, we defined what pattern classifiers are. Right? We had looked at the two block diagram model, that is, given a pattern, you first measure some features. So, a pattern gets converted to a feature vector, and then the classifier essentially maps feature vectors to class labels. So, as I said, the course is about classifier design. We have looked at a number of classifier design options as an overview. So, now from this lecture we will go into details. So, just to recap what we have done so far, we have gone through a general overview of pattern classification. A few points from the general overview that I would like to emphasize here is a classifier that we already looked at is the base classifier. For the base classifier, we are taking a statistical view of pattern recognition. Essentially, what it means is that a feature vector is essentially random. So, the variations in feature values when you measure patterns from the same class are captured through probability densities. And given all the underlying class conditional densities, we seen that base classifier minimizes risk. We saw the proof for the only minimizing problem is classification. We will see the general proof this class. So, base classifier essentially puts a pattern in the class for which the posterior probability is maximum, and it minimizes risk. If we have the complete knowledge of the underlying probability distributions, then base classifier is optimal for minimizing risk. There are other classifiers, for example, we see nearest neighbor classifier. Among the other classifiers, of course, nearest neighbor classifier will come back to again, but one other classifier that we have seen, which I would like to emphasize again, are a discriminant function based classifiers. That is, the classifier, we use H for the classifier function. So, H of x is 0 in a two class case, that is x is put in class 0, if some other function g w comma x is greater than 0. W is the parameter vector for the g function, g is called the discriminant function. So, we can design a function, a discriminant function g, or find the appropriate values for the parameter vector w among a class of discriminant functions, and a classifier of this kind h x is equal to 0 if g w comma x is greater than 0 is called a discriminant function based classifier. Sometimes it is simply called a discriminant function, or we say the classifier is the discriminant function, though g is actually the discriminant function. So, if a classifier is based on discriminant function, we call it discriminant function or a discriminant function based classifier, and so on. A special case of discriminant functions is a linear discriminant function, which also we considered, where h of x is simply sine of w transpose x. As I said, we normally take an augmented vector x, so that the constant in the linear form is incorporated. So, this is essentially stands for w summation of w x I plus a constant w naught, which can be viewed as a simple inner product w transpose x by always having an extra component 1 in the feature vector x, that is called an augmented feature vector. Then the w vector contains also the constant. Okay. So, essentially when g is a linear function like this, and h x is 0 if g x is greater than 0 otherwise. So, I can essentially think of h of x as sine of w transpose x, and such a classifier is called a linear discriminant function. We have seen this also in our first two classes, and this is another important structure for a classifier. Okay. We have also seen different approaches for learning nonlinear classifiers. So, we will consider all of them through this course. So, now in this lecture, we will start by giving you more details on the base classifier. So, we will derive the base classifier for a general m class case and for a general loss function, okay, not a 0 1 loss function. Earlier, we looked at it for 0 1 loss function and 2 class case. Now, we look for a generic m class classifier and a very general loss function. Before I start with the base classifier, this actually is a special case of what is called Bayesian decision making, okay, or the problem of decision making under uncertainty. Since this is more generally applicable, it is worthwhile spending a bit of time looking at what decision making problem is about. So, in a decision making problem, the task of course obviously is to make a decision. Okay. but the reason why it becomes a problem is that there is uncertainty about what is the right decision. Okay. What is the form in which the uncertainty comes up? Essentially, we want to decide on one of finitely many actions based on some observation. Okay. For example, in a pattern classification problem or in many other situations, you observe the state of some system, and based on that you should take an action. Say for example, a control problem is also a decision making problem. You look at the current output of the plant, and then based on that you have to take some control action. In the pattern classification context, for example, I look at the radar reflection signal, and based on that observation, I have to make a decision of whether there is an enemy aircraft coming or not. Or if I am thinking of identity authentication as a classification problem, I look at a fingerprint image and an identity claim, that is my observation. Based on that, I have to take an action of yes or no. Okay. The uncertainty is because the cost of my decision depends on some unknown state of nature, right. So, in the radar example, actually out there, either there is a enemy aircraft or there is no enemy aircraft. That is the true state of nature, but that state of nature is unknown to me. What I have is some observation, namely my radar reflected signal, which gives me some information, not necessarily exact 100% dependable information, but some stochastic information on the true state of nature. So, based on this observation that gives me some information on the state of nature, I have to make my action, and for a given action my payoff or cost depend on the actual state of nature which is unknown to me. So, once again in this example of deciding whether or not there is an enemy aircraft, based on my observation of the radar signal, I make a decision of sounding a alarm for bombing. Then whether that is right or wrong, and hence the cost incurred depends on truly whether or not there is an enemy aircraft. Okay. A loss function gives cost for each decision and every true state of nature. That is, if I take this decision and the true state of nature happens to be something, then I incur some cost. Since I do not know the true state of nature, I only have the observations, we need some strategy of decision making that minimizes some objective function, for example, expected value of the loss. Right? This is the kind of scenario we are in. So, to sum up, observation is the feature vector, the state of nature is the true class label for the feature vector is presented to be. So, based on my observation of the feature vector, I have to take an action. The action may be calling the class label, or to say no, I cannot classify, or many other things, but most of the time my actions are simply class labels. So, we need to decide on a class label based on the observation of the feature vector. Okay. So, with this general introduction, we now consider a base classifier, m classes and arbitrary loss function. Okay. So, let us denote the m classes by C0, C1, Cm minus 1. These are the class labels. So, what does that mean? Y of x, that is the variable we have been using to denote the class label of the true class label of a feature vector x. Because of random variabilities, y as a function of x could be random. So, but this variable y, which is a function of x, can take values as one of the class labels C0 to Cm. Let us say the actions that are possible for the classifier are alpha 0, alpha 1, alpha k minus 1. Of course, in general k will be m and alphas will be same as c, but let us just for now keep the notation different. So, the output of a classifier would be one of the alphas. That is why I said h of x belongs to alpha 0 to alpha k minus 1. So, the output of classifiers would be alpha j's, whereas the actual class labels will be ci's. The reason we would put different symbols is that essentially we want to think of the class labels as the states of nature, which is not known to us, and the alphas are the actions the decision maker. Alphas are what the classifier calls out. In general, of course, alphas can be class labels, but it is important to note that in general we do not have to have a m equal to k, right. We put k actions, k possible actions, that is k possible outputs for the classifier and m possible class labels. So, not only alphas need not have to be class labels, even k and m need not be same, right. Here is a simple example of why I may want to do it. For example, I may take k is equal to m plus 1, all the other alphas I make alpha 0 same as c 0, alpha 1 same as c 1. So, alpha 0, alpha 1 up to alpha m minus 1 will be class label, that is I am calling out the class, but I have one more extra action possible for the classifier, right. That will be alpha m, alpha k minus 1 will be alpha m, and alpha m may denote the decision of rejection. So, for example, I can design a classifier which looking at a class label it can say that yeah, I will take this looking at a feature vector, I can say okay, this is this class, or say that no, this feature vector does not look sufficient for me, I can't take a decision. For example, if I am doing a identity authentication system, somebody presents a fingerprint and an identity claim, I can either say yes, is a authorized user, or say no, is not an authorized user, or I can say this image does not look nice, so I do not want to take a decision. So, in practice what it turns out to be that maybe the image was not captured well. So, tell the user, can you please wipe your finger and give your fingerprint again. So, sometimes in certain situations having such a rejection option is useful. So, this is one example why the output of classifier may be different from the class label. There might be a few extra actions for the classifier. But anyway, for now when we are discussing the base classifier, we take k is equal to m and we assume that the output of classifier is also class labels. Okay. So, let the loss function L as you have already seen as two arguments, one is what the classifier says and one is the true class. So, L alpha j c k is the loss when the classifier says alpha I and the true class is c k. We, we assume that the loss function is always non-negative. Okay. Now, earlier we were saying L j comma k, in this particular derivation we are saying L alpha j comma c k. So, that we know the first argument refers to the output of the classifier and second argument refers to the true class. Okay. So, this kind of notation is a little easier to understand the arguments. As earlier, risk of a classifier h is the expectation of the loss. So, each classifier h, to each classifier h, I can assign a figure of merit which I call risk, which I write as R of h, which is expectation of L of h x comma y x, where the expectation with respect to the distribution of x and whatever randomness there may be in y of x. So, expectation of loss is the risk and the object of the base classifier is to find a classifier at decision rule h that minimizes the risk. Okay. Okay. Now, to derive the base classifier, let us say given a particular feature vector x, let us denote by R alpha I given x the expected loss when the classifier says I conditioned on x. It is given x and if I say alpha I, what is my expected loss? So, what does R alpha I given x correspond to? R alpha I given x is expectation of the loss, that is L of h x comma y x, but is not an unconditional expectation, it is a conditional expectation conditioned on h x is equal to alpha I, that is classified as alpha I, and conditioned on the random variable x. So, R alpha I given x is expectation of L of h x comma y x conditioned on h x is equal to alpha I and x. In a conditional expectation, if any of the conditioned random variables appear in the expectation, they can be replaced by whatever they are conditioned on. So, this is same as conditional expectation of h x can be replaced with alpha I, expected value of L alpha I comma y x, conditioned now only on x. Now, what is this expectation? This expectation of the random variable L alpha I comma y x with respect to the distribution conditioned on x. Y x can take values c 0, c 1 up to c m minus 1 with different probabilities. So, I can write this conditional expectation as this L alpha I comma y x will take value L alpha I comma c j with probability y x is equal to c j given x, right. When I sum it over j is equal to 0 to m minus 1, that gives me the conditional expectation. Now, we know what probability y x equal to c j given x is, that is what we call the postulated probability, for which we already have a notation q j of x. So, R alpha I given x now is summation j is equal to 0 to m minus 1 L of alpha I comma c j q j x. Okay. Now, using this we can now find an expression for the true risk. What will be the true risk? We have seen that R alpha I given x is expected value of L of h x comma y x condition on h x equal alpha I comma x, for which we have derived this expression L of alpha I comma c j q j x summed over j is equal to 0 to m minus 1. So, this is the case for L alpha I given x. So, in general we can also write this equation as R of h x given x is the same summation where alpha is replaced with h x, right. So, we can write R of h x given x as summation j is equal to 0 to m minus 1 L of h x comma c j q j x. So, this is the expression that we are going to use in deriving our final expression for the risk. Okay. Once we derive the final expression for risk, then we will see how to minimize this. Okay. So, risk as we know is the expectation of L h x comma y x. Now, as you know, any expectation can be written as expectation of a conditional expectation. So, that is how I have written R h here. The inner expression is expectation of L of h x comma y x conditioned on x. Now, if I take another expectation, it becomes the unconditional expectation of L h x comma y x. So, I have written the unconditional expectation, which is the risk R h, as expectation of a conditional expectation. What is the reason for that? The reason for that is I already have an expression for the inner conditional expectation, right. Inner conditional expectation, because the conditional expectation is only a function of x, right. I have an expression for this. Now, the outer expectation is the unconditional expectation of some function of x. So, I know how to do it because I know the density for x. Okay. So, let us expand this expression. So, the inner conditional expectation, which is conditional expectation L h x comma y x condition on x, is what we call R of h x given x, and the outer expectation is simply expectation of this as a function of x. So, the total expression becomes integral R h x given x into f x dx, where f x is the density function for x. Okay. This is just the conditional expectation integral. Okay. Because if x happens to be discrete, it will become a summation, but in general let us use integrals. So, so that we are essentially considering x, all x's to be continuous random variables. Okay. So, this is the expression for true risk. So, from this expression there is something that we can say. If there is a h, if we can find a classifier h such that R of h x given x is less than R of h prime x given x for every x and any other h prime, right. So, a h that minimizes every term in this integral, minimizes the integrand for each x, would be the optimal optimal classifier. Mind you, a minimizer of R h does not necessarily have to have the least value for every x. Minimizer of R h only means the entire integral should be minimized by changing the h. But in case there is a h which takes least value for each x, so that R h x given x is small for every x, then that will certainly be a minimizer of h. So, let us look for an optimal classifier by asking for each x, h x should minimize R h x given x. So, we want to choose a classifier h so that for every x, h of x is such that R h of x given x is smaller than R of anything else given x. Okay. So, that is certainly will be an optimal classifier, and let us ask, is there such an optimal classifier that we can find. So, this is the expression for h of x. Okay. So, if I want to say h of x is equal to alpha I, if I put h of x equal to alpha I in this, then that should be smaller than what any other classifier can assign to x. Now, every classifier, all it can do is, given an x, it has to assign one of the classes to it, right. And we are denoting the classes assigned by classifier by alphas, which brings us to the following definition. The best classifier will be one which assigns, let us define the classifier h b as follows. Given an x, h b of x assigns alpha I if L of alpha I comma c j q j x summed over j is less than or equal to L of alpha k comma c j q j summed over j. this will immediately mean HB is optimal. Why? Because HB assigns alpha I what or to x, what any other classifier can do is assign one of the other alphas to x, that is all any classifier can do. So, compared to assigning any other alpha, assigning alpha I is better, right, because by assigning alpha I, h of x given x is becomes smallest, right. So, if such a classifier would certainly minimize this integral, because for every x that classifier has the least value for all h x given x, right. So, this is our base classifier. So, base classifier is now simply defined by the base classifier assigns alpha I to x if L alpha I C j Q j summed over j is less than or equal to L alpha k C j Q j summed over j for all alpha k, for all k. So, of course, there can be more than one alpha which may attain the same minimum value, but that makes no difference. We can break ties arbitrarily. By arbitrarily, I mean we can have a consistent policy. If alpha 2 and alpha 3 both attain the same minimum value, then I will choose alpha 2 saying the one with the smallest index, or I can choose alpha 3 saying the one with the largest index. Any such arbitrary way of breaking ties is good enough, because that will make my classifier a function. Given any x, it unambiguously assigns a classifier. And the way we constructed it, it is clear that our HB of x given x is always less than or equal to R of h x given x for all h, because as we said HB gives alpha I, and what any other h can do is give one of the alpha k's, and no matter what alpha k this h gives, right, R h x given x for the base classifier is less than or equal to what any other classifier can achieve. Thus, R HB of x given x is less than R h x given x for all h and all x, and thus base classifier is the optimal. Okay. So, this is the general optimal base classifier for minimizing risk. Okay. So, let us take some special cases. We will start from this expression and explore base classifier for many special cases. Take m is equal to 2. If there is only 2, then the summation has only 2 terms, right, one for C0, one for C1. Okay. And h also has only 2 values, alpha 0 and alpha 1. So, what does the base classifier now say? HBX will say alpha 0 if L of alpha 0 C0 Q0 plus L of alpha 0 C1 Q1 is less than or equal to L of alpha 1 C0 Q0 plus L of alpha 1 C1 Q1. That is, assigning alpha 0 to x incurs less risk than assigning alpha 1 to x. Now, let us go back to our old loss function, where we normally put L alpha 0 C 0 to be 0, L alpha 1 C 1 to be 0, because if you take the correct decision, there is no loss. So, if we assume L alpha 0 C 0 is equal to L alpha 1 C 1 is equal to 0, then what does this mean? This term will drop out, this term will drop out. So, if I bring Q 1 this side, this expression is same as Q 0 by Q 1 is greater than or equal to L of alpha 0 C 1 by L of alpha 1 C 0. This is the base classifier for 2 class general loss function that we specified last in the last lecture. That time we said we will prove it later. So, from our general proof for optimal base classifier, we see that for the 2 class case, this is the optimal base classifier. Right? This is same as what we saw earlier, and now this completes the proof of that expression also. To consider another loss function, another special case, let us take the m class case, but now instead of a general loss function, consider a 0 1 loss function. Once again, this is the general expression L or alpha I given x is this. Now, if I consider 0 1 loss function, L alpha I C j is 1 if alpha is not equal to C j, and 0 if alpha is equal to C j. Now, alpha is are same as C j's for us. Now, we are considering classifier action same as whenever alpha is not equal to C j, the loss is 1. So, only those terms contained. When alpha is equal to C j, the loss is 0. So, this expression becomes summation over all j not equal to I Q j of x, because for a given x has to be from one of the classes, all the posterior probabilities together should sum to 1. So, sum mod j not equal to I q j x is nothing but 1 minus q I x. So, what does this mean? For the m class case and 0 1 loss function, my base classifier is for the m class case 0 1 loss function, we just now shown that R alpha I given x is 1 minus q I x, that the base classifier simply is if 1 minus q I x is less than 1 minus q j x for all j, then put x in alpha I. 1 minus q I less than 1 minus q j is same as q I greater than q j. So, even for m class case, if we have 0 1 loss function, all that base classifier does is assign x to that class which has the highest posterior probability. Okay. So, this is very straightforward. We have seen that in 2 class, that is what we have been doing. If you have a 0 1 loss function, you ask whichever class has the higher posterior probability, put it there. So, even for m class case, if we use a 0 1 loss function, what our general optimal base classifier tells us is that we have to assign x to the class with highest posterior probability. As I mentioned in the first lecture, this is the most obvious thing to do, right. Given x, if I can calculate the probability that x comes from class 1, x comes from class 2, x comes from class 3 and so on, then whichever probability is higher, I should put x there. So, our intuition is correct and that happens to be the optimal base classifier. This is the m class classifier for 0 1 loss function, which minimizes the probability of misclassification. These 2 special cases notwithstanding, this is the general, we have already derived this. So, the base classifier that minimizes risk, okay, under any general loss function is that given an x, the base classifier assigns alpha I to x, that is HB of x is alpha I, if R alpha I given x less than or equal to all alpha j given x for all j, where all alpha I given x is given by j is equal to 0 to m minus 1 L alpha I c j q j x. So, if I know all the posterior probability, if I can somehow calculate all the posterior probabilities given x, then I can calculate R alpha I given x, and hence once I can calculate R alpha I given x for all alpha I know which action to take. That is how I will actually implement the base classifier. So, to the implement base classifier, the statistical information I need to know is the posterior probabilities. Of course, I need to know the loss function. Then give me any x, for each of the alpha i's, I calculate this expression which gives me R alpha I given x. Then I will find out for which alpha is the minimum, and that is the class into which I will put x. Okay. I hope you understand that the only reason we are writing alphas for classifier outputs and Cj for the 2 class is that in the loss function arguments we know which is which, otherwise alphas are same as Cj's for us here. Okay. So, I can implement the general base classifier if I know all the posterior probabilities. Okay. So, this is the most general case. Here we are not even assuming that R L of alpha I comma C I is not equal to 0. Even if that is not equal to 0, even then we can calculate based on this expression. So, this is the optimal base classifier for minimizing risk for any general loss function. Okay. Now, what we will do is, we consider the 2 class case, take some specific class conditional densities and try to look at what the base classifier looks like. Okay. That gives us some more insight into how to calculate base classifier in specific instances. Okay. So, from now on, instead of writing L alpha I comma C j, we will simply write as L I comma j. By now, we have gotten used to understanding that the first argument is the classifier output and second argument is the class label. So, we will write L alpha I comma C j as L I j, and we will also assume that the correct classification as 0 loss. Okay. So, for a 2 class case, this is the base classifier. We know that q 0 by q 1 by Bayes theorem is same as f 0 x p 0 by f 1 x p 1, where f 0 is the class conditional density for class 0 and f 1 is the class conditional density for class 1, p 0 is the prior probability for class 0, p 1 is the prior probability class 1. Okay. q 0 by q 1 is same as f 0 p 0 by f 1 p 1. So, for the 2 class case, we will decide on class C 0 if f 0 p 0 by f 1 p 1 is greater than L 0 1 by L 1 0. Okay. So, given the loss function values, given the class conditional densities and prior probabilities, we can always calculate it. What we are now going to do is, assuming specific functional forms for f 0 and f 1, we will actually crunch this expression to see how such a classifier looks like. So, we will start with a simple case. We will assume that the feature vector is one dimensional, that is a single real number, we have only one feature and assume that both class conditional densities are normal. So, f I of x is 1 by sigma I root 2 pi exponential minus x minus mu whole square by 2 sigma square. This is the one dimensional normal density. So, f 0 is normal with mean mu 0 and variance sigma 0, and similarly f 1 is normal with mean mu 1 and variance sigma 1. Okay. Now, what is that we have to have? HBx is 0. If P0 F0, as you can see from here, what it means is P0 F0 L1 0 is greater than P1 F1 L01. Okay. So, P0 F0 L1 0 is greater than P1 F1 L01. Since ln or log is a monotone function, this will be same as if I take log on both sides, ln of P0 L01, those are constants, I will take a note separately, ln of f plus ln of f0 is greater than ln of P1 L01 plus ln of f1. What did I gain by choosing ln? Because the class conditional density involves an exponential, by taking ln, I will get a simple linear or quadratic expression in x. Okay. So, let us explicitly write this and see what it looks. So, we want ln P0 L01 plus ln f0. What will ln f0 give me? Ln of this, the constant term is minus ln sigma 0 and minus half ln 2 pi, and this will give me minus x minus mu 0 by 2 sigma j square, because ln cancels exponential. So, that is what I will get. This is the earlier constant term minus ln sigma 0 minus half ln 2 pi minus x minus mu 0 whole square by 2 sigma 0 square. Similarly, on the right hand side, where essentially where mu 0 came, now mu 1 comes, where sigma 0 came, now sigma 1 comes. So, if x satisfies this expression, then I will put x in class 0. Now, this expression can be further crunched. So, I get an x square term from here, x square term from here. The coefficient of the x square terms will be, see, let me write the next expression. So, I have half, if I take out, there is an x square term from here and x square term from here. Here I get 1 by sigma 1 square, here I get 1 by sigma 0 square. So, if I am bringing everything the left side, it will be half x square into 1 by sigma 1 square minus 1 by sigma 0 square. The x term will be, I get the 2 will cancel, I will get x mu 0 by sigma 0 square here and x mu 1 by sigma 1 square here. So, I will get x into mu 0 by sigma 0 square minus mu 1 by sigma square, and then all the remaining constants, all these constants plus what I get from here, mu 0 square by sigma 0 square and mu 1 square by sigma 1 square. Okay. So, if x satisfies this expression, then we say the base classifier will put x in class 0. Okay. So, I have rewritten this expression here. So, what we have done by algebra is to show that for the one dimensional normal case, both class conditional densities are normal, then base classifier will put x in class 0 if x satisfies this expression. What is this expression? This expression is simply a quadratic expression. What it means is that I am saying HBx equal to 0 if ax square plus bx plus c is greater than 0, where a, b, c are some constants, right, constants that depend on the underlying class conditional density, they depend on mu 0 and sigma 0 and also on the loss function and the prior probabilities. But essentially as a function of x, it is nothing but a quadratic. So, my base classifier now turns out to be HBx equal to 0 if ax square plus bx plus c greater than 0. What does that mean? In this case, the base classifier is a quadratic discriminant function. It essentially depends on a quadratic discriminant function. So, for one dimensional both class conditionals normal, the optimal base classifier is nothing but a quadratic discriminant function. Actually, in special cases, it may become linear. So, this is the general expression, base classifier assigns x to 0 class if this expression, this quadratic expression greater than 0. Now, let us take a special case where the two class conditional densities are such that their variances are same, that is sigma 0 is equal to sigma 1, and let us assume that the priors are also same, and let us say we are in 0 1 loss function. So, that L10 is equal to L01. Now, when sigma 0 is equal to sigma 1, the x square term drops off. Okay. When the x square term drops off, what I have is a linear function x That means now base classifier becomes a linear discriminant function, x by sigma square into mu 0 minus mu 1, all the others have gone except this term, that is 1 by 2 sigma square into mu 0 square minus mu 1 square. So, in this special case, if the two class-conditional densities are normal with same variance and priors are same and a 0 1 loss function, then essentially x has to satisfy this linear expression. Now, if I assume mu 0 is greater than mu 1, I can cancel the mu 0 minus mu 1 common factor without changing the sign of the inequality. So, that is if x is greater than mu 0 plus mu 1 by 2, then you put in class 0, otherwise put in class 1. Here we assume mu 0 greater than mu 1. We can actually see that this is quite a intuitively clear picture. Let us draw the two normal densities. We assumed mu 0 greater than mu 1. So, that is mu 0, that is mu 1. Both are the same variance. So, where will they cut? They will cut midway between the two means, right. Now, what is the base classifier? Because the priors are same and the 0 1 loss function, all it means is if whichever class conditional density is higher at any given x. So, if I am at this x, the f0 x has this much value, f1 x has this much value. So, because f1 is more than f0, I will put this in class 1. Okay. So, when both class conditions are normal and variance are same, essentially base classifier means till this threshold it will be put in the left class, after this threshold it will be put in the right class. Okay. So, that is why if the classifier base upper classifier turned out to be, if x is less than mu 0, if x is less than mu 0 plus mu 1 by 2, then put it in the mu 1 class, otherwise put it in the mu 0 class, right. As you can see this from this picture, this is the same thing that we showed about the error integral being same. The error integral is the area of these two types, these two sides. So, as we would expect, because variances are same, essentially the curves will cut midway between mu 0 and mu 1. So, till mu 0 plus mu 1 by 2 it should be one class, otherwise it should be the other class. Okay. That is what we have got, x greater than mu 0 plus mu 1 by 2, put it in the C0, otherwise put it in C1. So, we can say that this is a very intuitive classifier. So, the base classifier gives you what we will intuitively think is the right one. Let us take one more special case. Once again, this is my general classifier. Now, instead of assuming that the variances are same, now let us assume means are same and variances are different, right. Let us assume mu 0 is equal to mu 1 equal to 0, once again equal priors and 0 1 loss function. Now, what happens is the actual linear term drops out, only the quadratic term is left, right. It is half x square into 1 by sigma 1 square minus sigma 0 square plus minus ln sigma 0 by sigma 1, right. So, I can crunch this. So, it essentially means that x is greater than something, right, then x square is greater than something, then you put in class 0. I am assuming sigma 0 is greater than sigma 1. Once again, we can see that this is intuitively clear. What are we assuming now? Both the means are 0. Okay. One classifier has a large mu, another classifier has a larger variance, another classifier has another class conditional density has smaller variance. Because both the means are same, we assume that to be 0. The one that has larger variance, right, will go up at 0. So, it will cut the other one on either side symmetrically. So, from this point to this point, when x is between these two, this class conditional density is larger. At all the other places, the other class conditional density is larger. So, we will expect that for our final classifier should be something like if x square is greater than some tau, then I should put in the smaller variance class, in the larger variance class. If x square is less than tau, I should put in the other class, right. So, x between some minus something to plus something, it will be in the smaller variance class, and outside of that it will be in the larger variance class. Okay. That is exactly what we got. We are assuming sigma 0 is greater than sigma 1. So, if x square is beyond something, then I put it in the larger variance class. So, once again an intuitively very clear case. Okay. Now, let us consider, let us become more ambitious and consider the n dimensional case, once again normal class conditional densities. Now, that we have done for 1 dimensions, we can do it a little quicker. The n dimensional class normal density is given by this, the joint density will be 2 pi to the power n by 2 pi to the power n by 2, 2 pi to the power n into the determinant of sigma I whole to the power minus half, and exponential the quadratic x minus mu I transpose sigma I inverse x minus mu I. So, mu 0 and mu 1 as earlier are the means, and sigma 0 and sigma 1 are the covariance matrices, and now of course, x is a vector, so are mu 0 and mu 1, and sigma I will be a n by n matrix, right. Sigma, both sigma 0 and sigma 1 will be n by n matrices, they are the covariance matrices. Okay. Once again, this is my base classifier, it puts x in 0 if this expression is satisfied. Once again, taking ln will help me because the exponential will go away. So, what will be ln of f 0? There will be ln of this constant plus I get a quadratic form minus half x minus mu 0 transpose sigma 0 inverse x minus mu 0, and similarly on the ln f 1 side, right. So, that is what I will get. I got the quadratic form with mu 0 once and mu 1 once. It is like the old case, this is a quadratic form. So, there will be an x square term, there will be that is x transpose some matrix into x term. So, there will be a linear term in x and a constant term. If I bring all of them to one side, this is what I will get, right. There will be x transpose sigma I inverse minus sigma 0 inverse x, x transpose sigma 0 inverse mu 0 minus sigma 1 inverse mu 1 plus the constant term. As you can remember, in the scalar case, we got half x square into 1 by sigma 1 square minus 1 by sigma 0 square. Now, it becomes a vector case, that 1 by has become inverse of the covariance matrix, and this becomes a quadratic form, otherwise it is exactly same thing. Okay. So, once again base classifier is a quadratic discriminant function. So, whether in 1 dimensions or n dimensions, if the class conditional densities are normal, then whether or not the feature vector is for any dimension of the feature vector, optimal base classifier is a quadratic discriminant function. Okay. So, base classifier this quadratic discriminant function. Once again, we can do the same special case. If I take sigma is equal to sigma, then the quadratic term drops off. When the quadratic term drops off, I have some x transpose into some constant plus some constant greater than 0, then class 1. So, it will be like a linear discriminant function, right. Once the quadratic term vanishes, the base classifier now becomes a linear discriminant function. So, in the special case of sigma is equal to sigma, the base classifier becomes h by x equal to of j is greater than 0, where g x is w transpose x plus w naught. Okay. What is, so once the quadratic term drops off, this is w transpose x plus whatever is left is w naught. Okay. So, it becomes w transpose x, where w is sigma inverse mu 0 minus mu 1, and w naught is all the remaining terms. Okay. This is a linear discriminant function. So, both in 1 dimensional and n dimensional case, if the covariances of the two classes are same, base optimal classifier is a linear discriminant function, otherwise in the general case is a quadratic discriminant function. Okay. So, in this way, so we have seen examples of both 1 dimensions and n dimensions, only normal densities were considered. But this exercise, so basically what is that we have done? If you look at all our derivations, we start with a assumed class conditional density, then we say we use our basic derived base classifier h by x equal to 0 if this is greater than this, and then you plug in the expression for f0 and f1, and then with algebra you can ask what kind of expression is this in x, right. It could be a quadratic expression, it could be a cubic expression, it could be a linear expression. That is how we showed that Bayes classifier in different cases is either a quadratic discriminant function or a linear discriminant function and so on. Okay. So, Bayes classifier in the same way can be derived for many other class conditional densities. Okay. Later on maybe you will see a few more examples, but I hope the basic method is clear now. Depending on the nature of the densities, the final expression can be complicated. Of course, here they are exponential something. So, when I take ln, everything turned out to be just a quadratic form. With some other density, maybe some of the expressions can become a little more complicated. But the point is, given all the class conditional densities and prior probabilities and knowing the loss function, one can easily decide on the class of any given feature vector. We can actually analytically crunch and get a very nice simple expression. Of course, we could have actually calculated f0x, f1x and plugged it in that equation, but that involves finding exponentials. By doing all this algebra, we finally just evaluating either quadratic form in x or simply a linear function of x, which is much simpler than evaluating the quadratic form and then putting in one exponential, evaluating another quadratic form, putting in another exponential. That is computationally more expensive. So, what all this algebra has given us is that we can actually find the final form of how to decide on a class. Okay. Of course, we can always calculate P0, F0, P1, F1, no matter what F0, F1 was, and then we can get the Bayes classifier. What this example showed is in specific cases, right, checking this can be simpler than actually evaluating F0 and F1 at an x. Given full statistical information, okay, Bayes classifier optimal and we can always implement it. Because the next question is, who will give us the full statistical information? As I said earlier, we will see later on in our coming lectures how we can estimate the class conditional densities and hence posterior probabilities given the training data, that we will see later on. Okay. Now, there is another thing that we can see from what we derived today. So far in the beginning of this class, I have discussed discriminant functions, but we discussed it only for the two class case. We are saying a discriminant function Bayes classifier is HBx is 0 if some gx is greater than 0, where g is the discriminant function. Now, if I have multiple classes, how is the discriminant function idea is to be extended to multiple classes. When there are only two classes, depending on the sign of one function, I can say which class it is, right? Then the discriminant function Bayes classifier is very clear. But if I have multiple classes, I do not know how to extend it. I extend the concept of discriminant functions to multiple classes. The Bayes optimal classifier form that we got will immediately give us one idea of how we can extend discriminant functions to multiple classes. Okay. So, here it goes. The two class discriminant function as we have seen is this form hx equal to 0 if gx greater than or equal to 0 or otherwise hx is equal to 1. Okay. So, as I said, the Bayes classifier for multi-class case is a generalization of the discriminant idea to multiple case. We have not seen it like that. So, let us see it like that. This is the Bayes classifier for multiple case. Okay. This is the most general Bayes classifier. Okay. But if you consider say 0 1 loss function, then this thing is same as Pi Fi greater than Pk Fk. We have seen that essentially we have to say Qi greater than Qk for all k, then I put in class I. So, essentially in the 0 1 case, this general classifier turns out to be Pi Fi greater than Pk Fk for all k, which is same as ln of Pi Fi x greater than ln of Pk Fk x for all k. So, this is the general Bayes classifier for 0 1 loss function. I can view it as a discriminant function Bayes classifier as follows. Define g of x as ln of fi x plus ln pi. What is that I had to do actually? Ln pi fi greater than ln pk fk, right. So, this is ln pi plus ln fi greater than ln pk plus ln fk. So, I am saying define that as a gi of x. So, gi of x is ln fi x plus ln pi x. So, I have now m such functions. Instead of one function, have m GI functions. Now, what did the base classifier saying now? You decide on class I if GIX is greater than GGX for all j. Okay. So, in the 2 class case, I am saying the discriminant function based classifier is Hx equal to 0 if Gx greater than 0 for where G is a single function, that is called the discriminant function. Now, the base classifier for the 0 1 loss function case turns out to be there are some m functions Gix, if Gix is given in terms of the class conditional densities, but that is of no concern to us right now. Essentially, there are m functions Gi, and the base classifier is you decide on class I if the ith function's value at x is greater than value of any other function's value at x. If Gi of x is greater than Gj of x for all j, then you decide on class I. So, this is a general way in which I can use discriminant functions for the m class case. So, while 2 class case has only one discriminant function, for the m class case I actually have m functions, and I will make my decision by saying which function had the highest value. Of course, as in the base classifier, I have to break ties arbitrarily, but except for breaking ties arbitrarily, this is the generic form for discriminant function based on m class case. We will come to learning discriminant functions directly later on. At that time, we will see how to learn all these m functions, but this is a generalization of the discriminant function based classifier to the m class case. Okay. So, let me sum up what we have done this class. We have derived the base optimal classifier for m classes on any general loss function, and we have proved, we have stated what the base optimal classifier is, and then stated and then proved that it actually minimizes risk among all classifiers that have full statistical information. Okay. And this is the more general case. So, even though we proved earlier for the 0 1 loss function and 2 class case, this is for m class general loss function, and then we have seen many other special cases that come out of it. General loss function 2 class case, 0 1 loss function for m class case. For example, 0 1 loss function m class case gives you the same generic view of base classifier as the 2 class case. The 2 class case, I calculate the 2 posterior probabilities, and whichever class has higher probability I put in there. Even in m class, if I have 0 1 loss function, all I have to do is to calculate all the posteriors, and whichever posterior probability is higher, I put it in that class. Then we also seen how in a specific case one writes down the base classifier. Instead of calculating P0 F0 and P1 F1, P0 F0 x and P1 F1 x given x, which involves calculation of F0 x and F1 x, we have seen that in specific cases, given the functional form of the class conditional densities, the expression P0 F0 x greater than P1 F1 x can be simplified into a much simpler function of x to compute. Okay. For example, when the 2 class conditional densities are normal, then this is simply a quadratic expression in x instead of being exponential functions. And in this special case where the covariance matrices are same, it is even better, it is just a linear function. That means, base optimal classifier when the class conditional densities are normal turns out to be a quadratic discriminant function in the general case, and turns out to be a linear discriminant function in the case of equal covariances. Okay. Then we also seen that the general base classifier for the 0 1 loss function tells us a simple way in which to generalize the idea of discriminant functions. Okay. What we will do in the next class, okay, I will just give you a we will also maybe do one more example of base classifier to understand how this computation is done. But more importantly, now that we know the base classifier, the next question is to ask, can I calculate the error of the base classifier? As it turns out, given the class conditional densities, obtaining the base classifier is very simple, as we have seen. In the simple sense, I can always write the expressions and crunch them. But actually calculating the error that the Bayes classifier makes, which is the optimal error for the classification problem, and hence it is a good number to know as to what is the attainable probability of correctness. Very often calculating Bayes error turns out to be difficult. Okay. So, next class we look at some techniques for approximately calculating Bayes error. After that, what we will see is that even when we have full statistical information, even when we know all the class conditional densities, there is no reason why we should only look for risk minimization, right. There can be other objective functions. So, we will look at least a couple of other equally plausible ways of defining what an optimal classifier is. Look at what those classifiers mean, and hence see that Bayes classifier, while we say is optimal, is only one of the many different criteria that you can use. However, the reason why we emphasize Bayes classifier so much is that minimizing risk is often a very useful practice in machine learning and pattern recognition in general, and Bayes classifier is based on minimizing risk, and that is the reason Bayes classifier has a very important place. So, we will just see that there are other automation criteria, but and then get back to Bayes classifier and risk minimization. Okay. Thank you.